Good evening, everyone. Is my screen visible now? Am I audible?
Yes, sir.
Okay, I think we should wait for 2-3 minutes. Maybe someone else will join. Then we can start today's session. Good evening, everyone. Am I audible?
Yes, sir. Audible.
Okay. Okay, let us start today's session. I am Adnan Farooq Khan, PhD scholar from IIT Delhi, and today is our third problem-solving session for the course Advanced Power Electronics and Control, which is being taught by Professor Avik Bhattacharya. So, like previous two sessions, today also, like, I'll be going through this week's summary, that what has been taught in this week. Like in this week, Mostly sir covered like single phase and three phase converters and multi-phase converters, and in the later part of the week effects of the source inductance in was being taught for the single phase and three phase converters, which I'll go briefly through to brush up your concepts, so that will help you in solving the problems. Like today most of the problems will be numerical based, and I'll be discussing some problems related to what has been taught in the previous week, I mean this week, uh, and I won't be solving these assignment questions like assignment 1 and 2 because the solution of that has already been uploaded and it is somewhat detailed solution, so I won't be going through that. So today we'll be discussing some numerical problems related to single phase, three phase system, single phase AC to DC systems, and on these effect of the source inductance. So like I said, through this summary these concepts were shown. We will briefly go through them. So firstly, what was being taught in this week is like different types of rectifiers. uh, in rectifiers, as you know, we are having rectifier are mostly like AC to DC system. Where through rectifiers what we are be able to do, we are able to convert like AC to DC, and you know, like the supply that is available to us is either a single phase or a three phase system. So in rectifiers we'll be seeing like single phase or three phase rectifiers and their types. Like subsequently we'll be talking what had been taught to you was like uncontrolled ones and half controlled or partially controlled, you can say, and then fully controlled rectifiers was being taught. And what can be seen, like in both single phase and three phase systems, uh, like single phase and three phase system can have both half wave topologies, like which can only rectify a half wave, and there is a full wave rectifier which can have a split supply or a full bridge rectifier. I'll be briefly going through these, like what has been taught to them. I'll be showing the circuitry, and we'll be rushing towards the problems in the later part. As you know, like first talking about like uncontrolled, where the talking about this uncontrolled rectifiers, be it single phase or three phase, you can understand by this name, like uncontrolled, uh, where we are having an uncontrolled device like a diodes are used, because we don't have any control over their turning on and turning off, and they'll be turned on and turned off according to the circuitry, like how the voltage is implemented or the current flows through the circuitry. Will the diode get forward biased, will it conduct or not? And in half controlled, we have a combination of both the device, the uncontrolled as well as controlled. Let us say we have a full wave rectifier, full wave full bridge rectifier, where we are having four, in uncontrolled we'll be having the four diodes. However, in the half controlled or partially controlled, we'll be having like two diodes or two thyristors, and that will constitute like a half controlled rectifier. And for fully, like all the devices that are being used, we can control them, like we can turn them, they are controlled, like then we can see if they are only turn on, is they controllable, and or their turn on and turn off are turn off and turn on can be controlled. So coming like to the first part, towards my left, like the first picture that I am pointing my arrow towards, you can see this is a single phase uncontrolled half wave rectifier, and towards the right is single phase controlled like half wave rectifier. Like here in the uncontrolled one, you can see there's an uncontrolled device like a diode. We don't have any say like when it can turn on or turn off. It will only depend upon this supply and this load. and what will be the circuitry, like at that time, at what time that diode will turn on or turn off. In the SCR, like you know that SCR we can control its turn on, like we will be able to turn it on. It has a control turn on, but we won't be able to, like we don't have any control over its turn off. And coming to, like, what is a single, like, half wave? Because if you can see, look at this diode, see, like, this is a sinusoid. It is having a positive part as well as the negative part. When the positive half is implemented across, is implemented to the diode, like, we know that anode will be at a higher potential than this cathode. That means that this diode will get forward biased. When this diode will get forward biased, it will start conducting. So at the output we'll be getting only a positive half, and when this negative half will come, at that moment that diode will get reverse biased, and that diode will become open, and we won't have any voltage, like we'll be having a zero voltage at the output. That's why the half wave rectifier. This towards my right is still the half wave rectifier. However, we can control its turn on. Like if we don't want to turn it on at the 0 point, or omega t equal to 0, like we can turn it on at some alpha at which we want it to turn on. Because for SCR we are able to control its turn off, like at what time we want to turn on this SCR, that is up to us. So this is a controlled one, but still it can only have the half, only at the output we can only have the half, like a positive half, because at the during the negative, this diode, this thyristor will be off. So this was about the half wave. Now coming to the full wave rectifiers, we have a split phase. Like this is possible for the single phase supply, single phase, where we are having a transformer, and single phase is connected to a transformer, and the secondary of that transformer as a common midpoint, like, and we have two diodes. Like through this we are able to have that this load is connected to the midpoint, and across this load we'll be able to have both the positive as well as this negative waveform, positive as well as a negative half at the low. Similar, and this is an uncontrolled one, because like uncontrolled device diode is being used here. And towards my right is a full wave rectifier, and here the thyristors are being used, like as I had told already, we have a control over its turn on. So at this load we can have both positive as well as this negative halves, and we have a control over their turn on. That's why, like, this is a single phase controlled full wave rectifier. And you can see, like, these here, the transformer is being used, to have this full wave rectifier. I think these topologies are not that much used in practicality, in practical. And we move to the other topologies of this full wave, single phase full wave rectifier. Like the first image at which I am pointing my arrow is a full wave rectifier, but it's an uncontrolled one. Like it's a single phase uncontrolled full wave rectifier or full wave bridge, you can see, because here you can see an H bridge is formed, and it's formed of like uncontrolled device, diodes. And at the output we can have both positive as well as the negative half of the sine wave. Coming to the second, here as you can see, I had already told in the first slide, like these rectifiers can be uncontrolled, partially controlled, or fully controlled. As you can see this picture number 2, at which I am pointing my this arrow is pointed, you can see that the top two devices are thyristors and bottom two are diodes. You can see like some of the devices here used are controllable and some of the devices are uncontrolled. We do have a control over the turn on of these SCRs, but we don't have any control on turn on or turn off of these diodes. So these type of circuits are called like these are single phase, half controlled or partially controlled, full wave or full bridge rectifiers. As this is not the only topology it can have. We can have like one leg, like one top and one bottom of one top and one bottom both diodes, and here we can have second leg of thyristors. That can be another possibility of this circuit. And also we can have top two devices of diodes and bottom two devices can be thyristor. That is another possibility of it. And coming to the third one, like this is also a single phase full wave rectifier, but here you can see like all the devices that are being used here are controllable devices. As such, like this rectifier is known as single phase controlled full wave rectifier or full wave bridge. So this was about like single phase different topologies that detail the operations, how they operate has been taught by sir in detail. Like you can go through those lectures. And what was taught later on was about like three phase rectifiers. And in the three phase, like also we have a half wave or full wave rectifiers. Here you can see like the first picture is a three phase uncontrolled half wave rectifier, because like the devices that are being used, as I already told, are diodes over which we don't have any control of the turn on or turn off. And here you can see like the three phases are connected to three respective diodes, and each of the diode will only be able to conduct in the positive half. When these not only positive half, like these will be able to conduct when I'll later be talking about the conduction of devices, how you can see which of the devices will be conducting. But you can see like these diodes will be only able to conduct during the positive half, like about the period where they will start conducting. I'll be discussing that in detail. And similarly, that this second picture is a half wave three phase rectifier, and here you can also see, here you can see that the devices that are being used are thyristors, which are controllable devices. And because of that, this is like a three phase half wave controlled rectifier. Now coming to this like full wave rectifiers, in case of the three phase, like in three phase system we don't have any split way. As of I know about the literature, maybe there might be, but as of what I know, like these are different topologies that can be in three phase full wave rectifiers. Here like the first picture that I have, that is like you can see this is a three phase full wave rectifier. You can see like all the devices that are being used in the three legs are diodes, and that's why like we don't have any control over them. This is like an uncontrolled version of the three phase rectifier, as a three phase uncontrolled full wave rectifier. Coming to the second picture, you can see like the devices that are being used are all are these. You can see like in the second picture you can see like the top three devices are like thyristors over which are controllable, which we can have a control over. and we can like turn on as per our will, or whatever we need from this, what kind of a voltage waveform we want, or the output. We will turn on these devices accordingly. And you can see like the bottom three, these bottom three devices are diodes, which are uncontrolled. Like you can see like this three-phase rectifier, full wave rectifier is partially controlled or half controlled. Full wave, three-phase full wave rectifier. Coming to the third picture, you can see like all the devices that are being used are thyristors, over which we have a complete control. Like not complete control, like we can control their turn on, we have some control over them. That's why like three-phase controlled full wave rectifiers. Now like I had told you, like I'll be discussing in detail this, the conduction, like which of these diodes will be conducting. That I'll be showing this in for the single phase, and similar concept is for the three phase. Like some of the questions in the problems will be about that, and that will be like discussed in detail there. Like coming to this single phase full wave rectifier. Here like you can see we are having like a four diodes are being used. Like we have two legs, we have four diodes, 1 2 3 and 4, like 1 3 4 4 2. You can see like we want to see like the how the conduction will happen from one diode. Like from the commutation we mean like if one of the pair of diodes are conducting, like how it will be transferred, conduction will be transferred from one to another, from one device to another. That's called like commutation, like we'll be seeing. If you can look at this topology, you can see like this diode 1 and 3, their cathodes are connected to point P. Their cathodes are connected to point P, like and if you can see diodes 4 and 5, both of these anodes are connected to a common point N. So if you can see, we can, like I had told, how we determine how they will start conducting. Like if you can see what I was talking about, this 1 and 3, they are connected at a common point P. And if you can see diodes 4 and 2, they are connected at a common point N. So like this first picture can be redrawn as this picture. That's fine. That's fine now, till now. Understand? So these top two devices, what we call, like they have a common cathode, as you can see, like a common cathode. So we called it the common cathode configuration. And what happens, like we will see what will happen in case of a common cathode configuration. If you can see, and here what happens is like the diode with the highest anode potential will conduct. Like I'll make you understand what is what do you mean by that. Let us say this is a single phase source. You can see its one terminal is connected to diode 1 and other terminal is connected to diode 3. So let us say some single phase voltage is applied across this 1 and 3. So when there is a positive half, the positive part will be applied across this diode. Diode 1 anode will be at a positive potential and diode 3 will be at some negative potential. So diode 1 will have a higher positive will be at a higher positive potential than diode 3. So you can see, let us first talk about diode 1. When this is at higher potential diode, and you can see that point, this 1 will be at a lower potential, so this diode 1 will be forward biased. Fine. So this positive part will be implemented at this point P. As you can see that this anode of this diode 3 is at a lower potential than this point P, that diode 3 will be reversed biased. That is what we mean. Like amongst these two diodes, the diode with the higher potential will be conducting. The other diode will be reversed biased. So in the common cathode configuration, the diode with higher anode potential will conduct. So when this turns from like positive to negative, then you can see that this diode 3 will be at higher potential than diode 1. So diode 3 will conduct, and this positive higher potential will be at a point P, which will in turn like reverse bias this diode 1. So that was for this negative half. So in the positive half, diode 1 will conduct, in the negative half, diode 3 will conduct for this common anode. So now coming to the common cathode, to common anode, that was about common cathode. Like now coming towards this bottom two devices, you can see like their anodes are at a common potential, but their cathodes are at different, will be at different potential. And what happens in this configuration, that cathode you can see that cathodes are at a different potential, and the cathode with the lower potential will conduct. As you can see, let us say some potential it has. For the positive half, like the positive voltage will be applied at 0.4. Got it? Let us say there is some potential at point N. When this fourth potential, the potential at 0.4 is greater than the potential at point N, you can say that diode 4 is reverse biased. However, when at the same moment when there is a positive half, that is gives the like 4 the positive higher potential, like at point 2 we have a negative voltage that is implemented at this cathode, and even if there is a zero potential or some potential at point N, the diode 2 will start conducting. So you can see with the positive half, diode 1 and diode 2 will conduct, and with negative half, diode 3 and diode 4 will start conducting. That is how this conduction happens in this full bridge. And you can see similarly for a three phase, we will be having the three diodes with the common cathode configuration and three diodes with the common anode configuration. And amongst the three diodes, the diode which will be having the higher potential will conduct at any moment. Like we will be having the three single phases. We'll be having three single phases which will be 120-degree apart from one another, and the phase which will be having the higher potential, the diode of that phase will start conducting. And similar in the common anode configuration, the phase with the lowest potential will start conducting. That was about this conduction of these diodes. And it's all about the conduction, how these diodes will conduct. Now coming up to the second part, that is the load part. Like in the load, like different loads will be there, like can be there, like resistive, and there can be inductive load, like which is like most of the loads are inductive loads, because be it any wire or something with some resistance, there will be some inductance. That is like every practical load is mostly like in this inductive load, and there might be some capacitive loads like capacitive banks, and we'll be talking about RLE load, where we'll be having some battery or back EMF at the load, and also with that we'll having some resistance and inductance. And about this resistive load, it is quite simple. Like in the resistive load, whatever will be the load voltage, like the load current will follow the same will follow the same shape, and that is like that you might be knowing. Now I'll be discussing about this inductive load, where we are having inductive load with the controllable, like here you can, for this uncontrolled version, you can take alpha to be equal to 0, like it will start conducting from this point. From this picture here you can see, like I have shown here, you can see like this, that the sine wave shown with this gray is the source Vs, and with this black, the dark black, is the output voltage, and this blue one is the source current. As you can see, like these are the controlled devices, like we can turn them on at any instant. Let us say like we are turning on diode 1, and let us say 1, and these diagonal diodes we are turning at an instant alpha. So at an instant alpha, like these diagonal diodes will conduct, and the output voltage will have a voltage, will trace the voltage of this waveform. So at this dark black, as you can see, this black deep black color, darker black color is will be the output voltage. Like at the output voltage will be have from the instant alpha, where we trigger these devices. As you can see, like we are having a L here. So if for the sake, like we can say that L is very high, and due to that we can assume that the load current is constant, and due to that we can assume at a constant current, and you can see for that we'll be having this source current as a square wave, and we can have a DC output current, or DC current, that will be a straight line, like having the same value like as Is, peak of the Is, it will be a straight line. So in this, like the conduction will start from the alpha, but what had to happen at this pi moment, like these devices should turn off. But as you can see, like we are having an RL load, so you know, like in the inductor we cannot interrupt this current instantaneously, like it cannot be interrupted. So what will happen, like at the this after the pi interval, when this negative voltage is still, these the current will flow through these diodes will be forward biased, and what will happen, make these current will make these current flow in the same direction. So what will be able to have, due to this inductor, the current will have the same direction, and because of that thing, like we'll be able to have the negative voltage at the output, which shouldn't have had it been a resistive load. So due to this inductance in the load, we can get this negative voltage at the output. So now you can see, like at the output we have a voltage which has the positive part as well as the negative part. So you can say, if you can calculate the average of these voltages, you can see hadn't there been this negative part, the average would be somewhat higher, but because of this negative part, the average of this waveform will be lower. And when this inductance is completely discharged, and this moment, like other two devices will be on, so this will be the voltage waveform, like tracing from this point. So as I had already told, like if the inductance is very high enough, like the load DC will be continuous, like a straight line you can assume, and it will allow, due to this inductance, the negative voltage can also come across the load. So you can see what will in this here, you can see at the load we are having a negative voltage, but the current is still positive, because that inductor cannot allow like the change of current directions. uh, so you can see in this interval, like the power is negative. Because of this negative voltage, the power is negative, and hence we can say, like, with these devices can with these like controllable devices, we can have regeneration as well. Now here we had seen, like, because of this inductance, like we had this negative part of the voltage, and somewhat our average voltage magnitude at the output was decreased. So now we will look into, like, can we have still only the positive voltages at the output, and can we by somehow like clip this, or doesn't have or don't have this negative part at the output. So we can see here, if you can, sorry, so if you can see, like, we have now we have this a full wave rectifier, but it has one extra diode, that is like called freewheeling diode. You can see that is connected across this load, you can see, like, this diode. So what happens is, like, as earlier you see that at the alpha we trigger these devices, and the devices will start conducting. Like, it will trace this positive half of the sine wave after alpha, like output voltage will trace this positive half of the sine wave up to this point pi. So this means, like, up to this point, like, these devices are conducting, but as soon as this source becomes negative, what had happened, because of this inductance, in case of this inductance, like, output voltage was negative, but as soon as this output voltage will be negative, you can see that this diode will be forward biased, and, like, this load will get shorted because of this diode, and it will provide a path. What we needed is, like, a path for the inductor current to flow, like, the inductor current will now be inductor will be discharged through this path till this inductor current will be zero. We couldn't, like, interrupt this inductor current. We cannot, like, interrupt this inductor current instantaneously, or change its direction in instantaneously from positive to negative. So here you can see, like, after this pi, this freewheeling diode will become forward biased, and which will cause zero voltage across the load. So you can see, like, at the now you can see that output voltage is only positive, that is being traced by this darker black line, and you can see, since there is no negative part in the output, the output voltage, average output voltage, will somewhat increase. Since the output increases, like, our input remains will be is constant, input power is constant, but our here by our output increases as compared to the topology without this freewheeling diode. So you can see, that our power factor will also increase, like, which is like V out I out by Vs Is. Since our output increases, like, power factor will also improve. So the other thing is, like, you had, like, earlier seen, our voltage at the output was pulsating, like, from zero. If there's a, like, a diode bridge rectifier, it would have been with a resistive only role, it will be 0 to pi, then pi to 2 pi, like, it will have a very high ripple. However, like, if we want to reduce our ripple, have a constant sort of a voltage at the output, what we do is like we have a capacitor across this load resistance. What will happen here is like at for the first, this is like this waveform is shown for the steady state. At first instant, like this capacitor will be charged. Let us say now this capacitor holds this amount of charge, where I am like pointing this pointer. So as you can see, now there is some voltage or put at this output. Now these diodes, if you can go to the common cathode configuration, now there is some potential at this, let us say this point is point P, there is some potential at this point P which is equal to this voltage. Now this diode will only be this diode will only start conducting once this input voltage will be higher than this voltage, like this output voltage or the voltage across this capacitor. So as soon as this input voltage, which is traced by this gray line, will be higher than that of this voltage, that current this diodes will start conducting. As you can see, that are current that are this I will be will start flowing. And as soon as like voltage tries to decrease, like these diodes will be reversed biased, and you can see that now in the later part, like this capacitor will try to discharge through this resistor. That is why like it will depend upon this slope, like this slope of this V out will also depend upon the size of the capacitor. Higher the size of the capacitor, higher will be, lower will be, less will be its slope. Like it will have it won't like discharge very it will take more time to discharge. So you can see that this voltage will decrease slowly up to this point, and after this point, if you when we will see this for the second half, you can see as the voltage goes beyond this point, it will start conducting, and current will be only this portion where the voltage, input voltage, will be higher than this capacitive voltage. Here what we are able to achieve, you can see that the ripple across this output voltage is somewhat is decreased. But the disadvantage, you can see here, we have a current like that is having a peaky nature, and due to like this peaky nature, this will be having like very high THD, and this supply will be connected to some other devices, which I had also already discussed in the previous week. At the point of common coupling, there will be some other devices that will be connected to this point. Having this sort of a current flowing through the source will have like a detrimental effect on other devices. So we don't want like this kind of a current, but also we want like this kind of a voltage which would be having a ripple. That you will see how we are able to achieve that in subsequent classes. And for this I'll leave it here. Like because of this capacitor, have a capacitor at the output, we are having like a current with the peaky nature, and this current will be having very high THD. So you can see that I had talked about this output voltage will be nearly constant, but the input current will be highly distorted, which is not good. So this was about this capacitance at this load side. And now also in terms like have a capacitive load as well, like a similar kind of thing will happen. Coming to this other kind of a load, like we are having a RLE load. Like in this kind of a load, you can see we have a battery or at the load, or we can have or this can be a DC motor, that this will constitute the back EMF of that motor. here you can see there will be some potential applied to this cathode, which is dependent on this, what is this E part. Here let us say, if you can see this straight line that has been traced is E portion. Let us say it is 10 or 20 volts, and we have a sinusoid single phase supply applied at the input. So as long as like this sinusoid is below 20 volts, this diode will be reverse biased, it won't start conducting. And as soon as this input voltage is higher than this output voltage, this diode will start conducting. That is this. And you can see the point of natural commutation for the diode is changed by some angle. Here it is represented by gamma. So you can say now the diode won't start at this from 0, it will start at the gamma, and it is dependent on this E. Higher this E, the more will be this gamma angle. So after this gamma, like our diode will start conducting, and due to RLE will be having like this current of a current, and as already discussed, due to this L at load, we can have a negative part of the current, negative voltage at the output as well, as discussed earlier. That will be similar here. Only the start of this is delayed due to this E. Higher the E, this higher will be this gamma angle, and here this beta is the total is the point at which this conduction will stop. So this I had already discussed, like here this load can be DC motor or a battery bank with some resistance, and due to this RLE, due to this E, the point of this natural commutation is changed. So next, what was taught is like effect of the source inductance. As such, like what is like the source inductance? Let us say at the source we are having a transformer, it will have some leakage inductance, or as you know, like at the source they will be having their own impedances as well. Like they are mainly this inductive impedances. That's why like they'll constitute like we talk about them like as a source inductance. So we'll be looking into what will be the effect of this source inductance on these like rectifiers. So as you can see, like this is the full bridge diode rectifier without a source inductance. Here we haven't taken the source inductance into the consideration. So here we have assumed like that the output is highly inductive, like the load output current is constant. So as you can see, like this is the output voltage that will come like the positive half, and the negative half will be inverted at the output, like it's a full wave rectifier. And our input current will be a square wave, like in the positive half D1 and D2 will conduct, and in the negative half D3 and D4 will conduct. So our source the grid current, can say grid current or source current, is like a square wave. That is in the practical circuit without any source inductance, when we don't take any source inductance into consideration. Now we will talk about this source inductance. Let us say there is some inductance due to source, Just a minute. So here we are taking, let us say there is some source inductance which we have like shown as an inductor here in the source, on the source side. So like already this inductor won't allow what you had seen earlier, like current was changing from this positive to negative instantly at this moment, at this pi instant or at this 0 instant, from positive to negative or negative to positive to negative at pi and negative to positive at 0. So due to this inductance, it won't allow certain change in the current. So you had seen, like in the positive half, diode 1 and diode 2 will be conducting, and in the negative half, like diode 4 will be conducting. But due to this inductance, you can see that for a certain portion of time, like both all the diodes are conducting, and due to this you can see that some part of the current will flow through one leg or some with through other. You can see like all the current, all the diodes will be conducting, and what the effect of that would be, like you can see if that diode 3 and diode 2 are both conducting, you can see that our load is getting short circuited, like there will be a zero voltage across the load. You can see due to this source inductance, for this period of time till our current is transferred from one set of a device to other set of devices, like there is a portion where all the devices are conducting. In this portion, like this output voltage will be 0, and as soon as like this current is transformed one set of device to other, the output voltage, there will be output voltage, as you can see. And similar thing will happen at this, after the pi interval. You can see that at this pi moment, now current will begin to decrease, that this current starts to decrease, and after that this current is transformed from one side of devices to other, like there will be some voltage at the output, and this is therefore there is some voltage at this output, and their output voltage will there will be voltage at the output. So due to this source inductance, there is some portion where the output voltage becomes 0, and what can happen of this, due to this, like instead of having a full wave, now there are some portion where there is no voltage, and you can say because of that, like our average output voltage will somewhat decrease. So talking about this effect, like this portion where all the devices conduct, like during the commutation, let us say like this has been represented by mu. So the effect of here we can see, like applying this equations of this inductances, like has been taught by sir. You can go through the in detail. Like the equation here is cos mu is represented by this equation, as you can see here. This from this equation you can see as ls increase, like so source inductance will increase, our commutation period will increase. Like this can be seen that it will take, since the inductance is more, it will take some more time to the slope will decrease, and it will take some more time to transfer this current from one set of devices to other. Also, you can see if from this equation, if this output or load current is higher, it means that this current has to transfer from one level to another higher, from one higher level to other higher level. So it will be taking some more time, and which will in turn increase this commutation period. On that also I had, you can see, you can deduce this from this equation like this top equation. So also, like I had already told you, because of this zero portion in this output voltage, somewhat output voltage will be reduced. You can like see from the equation, this second equation, because of like output voltage, due to this overlap or commutation, like the second term comes into being. Had there been no ls, like V output will be 2Vm by pi, which is like which is the equation for the full wave rectifier. But due to this commutation, this second term comes into picture, and due to that, this output voltage will average output voltage will decrease. And you can see its dependence, like it has a direct dependence on this ls, and higher this ls or load current, that lower will be our output voltage. So yeah, this was like a brief summary. uh, this was like the brief summary what had been taught in this like week. Also, like sir had taught about this some multiples converters that was not discussed in much detail, like that will be discussed in this week, and for like to see, read the like learn about these multiples converters in detail, like you can refer to book like High Power Converters by Binwu. So yeah, this was about what had been taught in this week. Now we'll be going forward with our problem solving. So yeah, coming to the first problem, sorry. So yeah, everyone is there now. So coming to the first problem. So you can see, like the first problem is like these are numerical based problems. I'll be discussing with you like how to solve these problem and how to approach them, and you can then this will help you in solving your the assignments that has been given to you. Like the first question here, what is given is like a three-phase diode bridge rectifier charges a 240 volt battery. uh, Input voltage to the rectifier is a three-phase 230 volt 50 hertz. Like it is given, like the input voltage is 230 volt and 50 hertz. Like when the input voltage is 230, so you can see like this is the phase voltage. Had it been like 400 or 415, you can see that is the line voltage, and this is the frequency of the input. And what is also given is current limiting resistance in series with the battery is 8 ohm. So at the load we have a battery and series resistance, and also it is given like there is we have an inductor makes the load current almost ripple free. So we can see that the load is an RLE load. So here what needs to be calculated, so what will be the value of current distortion factor and input power factor. So what we have to calculate is a current distortion factor and input power factor. Here like options are given, like A, B, like 4 options are given. I won't tell you to guess because this is a numerical problem and we have to approach and I'll show you how to solve this problem. Yeah, like someone has solved it. I think it's uh, and Disha is saying like it is a one option. Let us see how to solve this uh, problem. So so you can see what is given is like we are having a three-phase rectifier. So here you can see like we have a three legs and each leg is connected to one phase. So like we had discussed the conduction in the single phase, like on the similar note we can see the conduction in this three phase. You can see the cathodes of top three devices are connected to point P and the anodes of bottom three devices are connected to point N. So we can say like the top three devices are in common cathode configuration and bottom three devices are in common anode configuration. And like as I had already told, like for common cathode configuration, the diode with the highest potential will start conducting, and in the common anode configuration, we can say like the diode with the lowest cathode potential will start conducting. Here you can see like with these gray waveforms you can see like three waves are like traced, like this is VAN, this is 120 degree apart is BVBN, and then VCN is this one. So you can say from this portion 1 to 3 VAN is higher than VBN than VCN. So in this portion 1 to 3 here diode 1 will start conducting. For diode 1 will start conducting, like because the phase A, the potential of the phase A is higher than B and C. For 3 to 5, like B phase has the highest potential, as such diode 3 will start conducting, and 5 to 1 you can see that C phase is having the highest potential, like 5 to 1 you can say that you can see that diode 5 will start conducting. So here what is seeing like this 1 3 5, it is like this point of natural commutation, like from point 1 diode 1 will start conducting, from point 3 diode 3 will start conducting, from point 5 this 5 diode 5 will start conducting. Similarly we can look into this negative side, like for these bottom three devices which will start conducting. Here we know that which has the lowest potential, the common anode configuration, which has the device which has the lowest potential will start conducting. So you can see at this point 2 you can see that C is having that lowest potential as compared to A and B. So here you can see that with the C phase, like diode 2 is connected, so here diode 2 will conduct, sorry. Here you can see like after this point 4, like this A phase is connected, so here this this diode 4 will start conducting. Here from 6 to 2 this B phase is having the lowest potential, so diode 6 will start conducting. So yeah, so you can see that from point 1 to point 2 there is a like a 60-degree interval, like, or from 1 to 3 it's a 120-degree interval. So yeah, now if you can see any of this interval you can take. Let us say let us take any of this interval. Let us take this 60-degree interval. You can see from 2 to 3 you can see that diode 1 is, we have a positive of diode 1 and we have a negative of this. The C is conducting here, where my arrow is currently moving. Here we have A phase is on and C phase is on, and you can see we have what voltage will be having across the load is VAN minus VCN. So we can see that at the output what we get is a VAC. Similarly, you can see for other things like in from 3 to 4 there will be VB and VC, like VBC across will be across the load. Here you can see that the load voltage will be having the 6 pulses of 60 degree, and the peak this will be the the peak of this will be the peak of the line voltage, which will be around like 560 to 580. If it is a 400 volt line to line, that peak will be around 560, or 450, that 586. So yeah, we'll be having like a 6 pulse voltage across this load. Also, you can see what about now we'll be talking about the current. This blue, as we know, like what has been given in the question, like the output, the inductance is so high that the current is constant. So you can see from the interval, now we'll be talking about this source current. Let us now take this phase A. Like when the diode first will be conducting, like the source current for this phase A will be positive, and when this diode 4 will be conducting, it will be negative. So you can see from the interval 1 to 3, diode 1 is conducting. So yeah, here this IA, like current through phase A, is positive. You can see they from the interval like 3 to 4, that diode, neither diode 1 or neither diode 4 is conducting, so no current will be through phase A. And you can see from the point 4 onward, 4 to 6, like diode 4 will be conducting, as such will be having a negative current. So you can see the wave shape that is being formed here is somewhat a stepped wave, like what we call it is a Cauchy square wave. This is not an exact square wave. There are some portions here where there is a zero interval. So this wave is called a Cauchy square wave, and this wave, since like this is by for this three phase, this wave, if you do the Fourier analysis, it will have its fundamental and other harmonic components. You can see, since like this is being formed by this diode bridge rectifier, the fundamental will be in phase with the voltage. Like let us say VAN, like you can see it is starting from 0 point, the current is forming, and you can see that the 0 point is at the center of this zero interval. We know that this interval is of 60 degree, 60 degrees, so it is at the center there. Like we can see that this portion is like 30 degrees, like this theta is around 30 degree. You can see that. So we know like this is a Cauchy square wave, as I had already told you. Like we can calculate the RMS of the fundamental as well as the total RMS of this Cauchy square wave. So these are the equation. Like the first equation, it will give us the RMS current. Here the theta, I had already told you, is the like 30 degree, because like this from zero portion will be the half of this zero interval. Zero interval. And also we can calculate the RMS of the fundamental, which will be given by this equation 2, like the A1. And here when we put like theta equal to 30 degree, we can have these equations for the RMS and RMS of the fundamental component. So yeah, like we know that the displacement factor is like RMS of the fundamental divided by the RMS. Like if we put up these, if you put up the values, like we have been given, like this output current already is being given. No, as you can see, like it is a division. you can see that these factors will cancel out. What we'll be getting is this factor will be equal to this part. So our displacement factor is 0.95. Now coming to the power factor, we know that power factor will be displacement factor into the cos phi 1. Now as I had already told you, you can see that the fundamental of this current and this voltage are in same phase, like they start and they have a zero crossing at the same point. So phi 1 is 0. So what we have here is like a power factor will be same as the displacement factor. So that is the uh, uh, displacement factor is a distortion factor, current distortion factor. So here like the option A is correct, that current distortion factor and power factor will be same as 0.955. Coming to the second question, what is given here is a three-phase 3-pulse converter is operated from a three-phase 230-volt 50 hertz supply. As you can see here, previously I had told you that is a 6-pulse converter, that was a full bridge. Now here what is given is a 3-pulse converter, and you can like infer it from it. It is a half wave, 3-phase half wave rectifier, 3-phase half wave converter. Also like what is given is we have a load resistance of 10 ohm. What we have to find is find the value of the firing angle if an average output voltage is 50% of the maximum possible output voltage required. So what we have to find is, with this three-phase converter we will be able to have some maximum amount of this output voltage, average output voltage. Now because like these are, we have to find the value of the firing angle, that means like these are the control devices. So we have to see where we want to turn on these devices so that we our output voltage will be 50% of the maximum output voltage. So what we require is the 50% of the maximum output voltage at the output. We have a certain options like are given here. We will look for it. What is the correct option for this? So yeah, I was talking like there is a three-phase is there, and we have a three half bridge three-phase converter is there, and we have a control device. You can see like the waveform, because of this three-phase we can have VAN will start conducting, like this point is these among us these diode will conduct, which will have the highest potential. Had these devices turned on at their natural commutation, like will be like this gate will be continuously given to them, like no, the topmost diode will be conducting when the A phase will be having the highest voltage, that is in this portion. Similarly, second diode will conduct when B phase will be having highest potential, and similar to that the C phase. Here you can see that the voltage waveform that is being traced by this black one will be the output voltage across the load here. So the maximum voltage that we can get is like here when we have a zero firing angle, and it is given by this equation. You can see in detail how we come up with this equation, and for the three phase you can go through the lectures and notes that have been provided, and this is the equation that you will get. So with this you can get the maximum output voltage. Now what we require is like the 50% of this maximum. What we want to have is like this 50% of this. So now we have to like turn on these devices at some alpha or at some angle, so that we can have the voltage at the output is 50% of this maximum voltage. Now let us first see. Now if the alpha is less than pi by 6 or 30 degree. So for any kind of a load, like if we have a RL load, the equation, like the thyristors won't start conducting from this point, they will start conducting from an alpha, and it will trace this output voltage, will trace this waveform. And similarly B will start conducting from this point and C accordingly. So the equation, like for this alpha less than pi by 6, we have is given by this equation, 3 root 3 Vm by 2 pi into cos alpha. However, we know if the however we know, like if uh, the alpha is for RLE load, for RL load we had already seen that the output voltage can be negative. So if output voltage can be negative, but if we take that into the consideration, so this equation holds true for that. If we put that into here, like the output will be here, and what we want, the output is half of this. If we put that here, alpha will become out to pi by 6 had this been RL load. But what we are given is like it is an simple R load, and we know with R load the voltage cannot go negative. So if the pi is greater than pi by 6, at pi by 6 what we get is a 0 here, like it will trace this point and start at this point. But after pi by 6 this uh, pi by 6 alpha, what we get, there is some had there been an RL load, we would be having some negative part here in the output voltage. But since there is but our load is purely resistive, and resistive load, for the resistive load we have this some portion for this alpha greater than pi by 6 where we have a 0 like voltage. So you can see here there will be some part where output voltage will be 0, and it will trace like this output voltage. Like if you calculate the average out of this waveform, like it will be given by this equation, because our what is being asked in the question is our load is resistive, and what we want have, so what we have to use is we have to use this equation, because the idea that needs that we had to understand from this question is to take into the consideration the load resistive. Like we know for the resistive load some part can be like negative, like for resistive, like we cannot have this negative voltage, and therefore our output equation would change. So we have to take this equation, not the first one. So if we now substitute, like V out is half of this V max, and if we substitute that here, what we get is alpha, and we know that V max is given by this equation and V out is given by this equation, and if we use V max by 2 here, what we get is alpha will be equal to 67.9 degrees. So that is the answer to this question. So I think we'll take 5 minutes break here, and then we continue with other question. Is that fine? And in the meanwhile, if someone like is interested, in the meanwhile he or she can like start doing this question and can tell what is the answer for this. Is that fine? Like 5 minutes break, like we'll be joining back around 8:25. Am I audible to everyone, or is there someone there or not? Hello? Okay. Okay, let us take a 5-minute break and we'll start again. Okay, let us start. So coming to the third question, what is given is like a 230 volt 50 hertz 1 pulse SCR converter is triggered. Firing angle is given 40 degrees, and what is given is like load current extinguishes at 120. Like alpha is given like 40 degree and beta is also given. What we have to find is average load current for R 5 ohm and L is 2 millihenry. Like I think one of the students had already solved this, and see option. Let us find out what is the answer to this question. Here what we can see is like we have a load RL load we are having. Like I think some other student are also like solved this. See, so here you can see what we have is a one pulse device here SCR, and you can see since this is the only one device, it's a half wave rectifier, half wave. You can see this bridge, and we have an input, and you can see like at the alpha instant we are turning on this device, and the device will start conducting, and at what is given is at this, and from alpha the current will start rising, and what is given is at beta the current comes out to be 0. So current extinguishes, it becomes 0. So we are given alpha as well as beta. Like this is 40 degree and this is 120 degree, and what we need to calculate is find the average load current. So if we are able to calculate what is the average voltage, and we divide that average voltage by this resistance, we can get the average load current, because uh, average load current is a DC current. In that DC part, like this inductor won't come into play, like it will offer no impedance to the DC. We know like the impedance offered by this inductance is omega L, and you can see like omega L is 2 pi f into L. Since that DC frequency to the DC is 0, like impedance offered by this is 0. So if we are able to calculate this voltage and we'll divide that voltage by R, we can have this output average current. So this output voltage for this is given by this equation, like root 2 Vs by 2 pi cos alpha minus beta, and if we know the alpha, we know the beta, and if we put the values of the alpha and beta in this equation, like we will get the output voltage around like 65.54 volts. Now we have, what we have to calculate is output current, right? I had already told only the resistance will come into the picture for this average output current, and we'll divide this average voltage by R, and R is also given to us like 5, I think 5 ohms, and if we divide this by 5, we will get a current of 13.108 amperes. That is the answer to this question, 13.10 amps. Coming to the fourth question, which of the following options denoted the advantages of the freewheeling diode in the rectifier circuit? I think like we have discussed this during this the revision of the previous what had been taught in the previous week. Freewheeling, like input power factor is improved, load current waveform is improved, input power factor and load current both are improved, or either of them are improved. Like, can anyone guess what can be the answer to this question? Like one of the students has answered it, or okay, others are also answering it. Like we'll see about this question. And already I had discussed here. Also, I'll try to explain what is happening is when we have a, let us say, RL load. If we don't have this diode, what would happen is we can have some negative portion of this voltage because of this. because if we don't have this diode, what would happen because of that negative portion? Our average output voltage would decrease. When our average output, that is like a drawback of that, if we don't have this freewheeling. Now when we have a freewheeling diode, what happens is, when this output voltage tries to be negative, this freewheeling diode gets forward biased, and because of that our load is current, inductor current flows through this diode, and the energy is dissipated, whatever the energy that is stored in this inductor is dissipated across this resistor, and during this period of time that load is shorted, and because of that we get a zero voltage across the load. So for due to this freewheeling diode, what we are able to achieve is zero voltage for some period of time, and due to this zero interval, the average of the output voltage would increase as compared to without to the output voltage of the circuit without freewheeling diode. And when our output voltage increases, you can see like our power factor would increase, because our source is same. So power factor is, if you can see, VSIS by Mm, we out I out by V9. As our output increase, our power factor will obviously increase. So you can see, because of this freewheeling diode, as our load is not doesn't go negative, like our average is increased, which improves the power factor. Also, what we can see, you can see, because of this freewheeling diode, the output voltage across this inductor would be less, and what we have is a lesser slope which would across the inductor, which would in turn the current that will be through this would have lesser ripple, which would in turn improve the waveform of this output of the output current as well. As such, option C is the correct option for this. Now coming to the fifth question. A one pulse SCR controlled converter is triggered at an angle alpha, and the load current extinguishes at an angle beta. Then what will be the circuit turn off time if the load is considered as an RL type of a load? Here, some options are given here. Also, some one has given some option. We'll see if this is correct or not. So here there are many options, there are different options from the different students. Let us go into the detail of this question. Here what is given is like a single pulse SCR circuit. We know that what is given is the device will start conducting at the moment we give it a gate pulse that is given at this alpha. So the device will start conducting, and as we know, we have a load that is an RL type of a load, and because of RL load, after this pi interval, as the current through this inductor won't change instantaneously. There will be some negative voltage also at the output. Now as soon as this output current comes to be zero, the SCR stops conducting. So beta is the angle at which this current will stop. So you can see that our device is conducting for a period of beta minus alpha, because it started conducting at an alpha and stopped at beta. Now you can see from alpha to beta it's only conducting. So we can say our our device is turned on only for beta minus alpha period. Now we can see the whole conduction period one conduction period is from 0 to 2 pi. So as you can see, whole conduction period is from 0 to 2 pi. You can see now for the off what we'll be having, we know that on it will be for beta minus alpha. Now off it will be from 2 pi minus beta minus alpha. Now if you can solve this theta, as you know, is omega t. Here the off period, from here what we can calculate is t off. So t off will be equal to 2 pi plus alpha minus beta divided by omega. So the option B is correct. Coming to the sixth question. What is given? A three-phase full converter bridge is connected to supply voltage of 230 volts per phase and a frequency of 50 hertz. Like we have a three-phase full bridge converter. What is given is a source inductance is like 4 millihenry. Source inductance is given to us. Also, what is given is a load current, that is 20 amps. Also, what is said is like the load consists of a DC source of internal EMF 400 volts. Like we are at the load, we are having EMF of 400 volts and a resistance which has an internal resistance of 1 ohm. So as we know, due to the source inductance, and what we have to calculate is the overlap angle. So as we know, due to this source inductance, there will be some commutation period or overlap period. uh, so here what we have to calculate is that period, for how much like a theta will be having the overlap. So we'll be going through this question. See, and as I already had told about this three-phase uncontrolled rectifier, where I had told about this diodes. Here what we'll be talking about this is the SCRs. Here also, like we can see the common cathode and common anode potential. But here as I already told, this 1 2 3 4 5 6 would determine the natural commutation. Had there been the diodes, they would have started at 1. We will see for the top 3 which of the SCRs or diodes will be at higher anode potential will start conducting. Now for this what we can do is we can now we are turning on these devices at a certain alpha, which is denoted here from one position, like from this natural commutation point where we turn on the device is the alpha. So here after alpha, like it will start conducting, and it will conduct till, like for the other device it will be start conducting from like 3 uh, no, like 3, and it's a alpha from 3 point. From similar thing will happen in the negative part, like this part is like a alpha portion. So here you can see, as you can see here for the 6 pulse, you can use the similar analysis as we had done earlier. We can see which of the diodes are conducting in the interval. Here you can see, like this is the voltage that will be like output voltage waveform will be of this shape in this converter. Here also, as we will change the alpha, the shape of this output voltage waveform will change. This is alpha. If we have a alpha at 60 degree, then it will start from here and will go here and here. And if the alpha is greater than 60, we can have the output voltage positive as well as negative by changing the alpha position. Now what we want to do, this was like Now what we will see is uh, this without how now what we will see how the currents will look like for one phase of this converter without the source inductance. So here you can see like when for the A phase, like this SCR1 will start conducting at an alpha from one position. It will start conducting till that B voltage for the B phase, like 3 is triggered on for this from this third point, like for alpha. Till then this SCR1 will conduct, so we'll be having a positive current for this period. Similar to that, when we have this we have to see the current will be negative when SCR4 is conducting. SCR SCR4 for the diode bridge, it should have conducted from here, but it will start conducting at an alpha from the 4. So here from here this is start conducting up to this point, so here the current is negative. And you can see that if you see the fundamental of this, you can see it already been discussed that the wave shape of this current is a quasi square wave which will have a fundamental, and you can see that fundamental will have a phase shift of an alpha from this voltage, because we are turning on this devices at an alpha. Had there been a diode, so this would have coincided. So this like the point 0 of the fundamental and this voltage of the phase will be at an alpha degree from one another. So now coming when we have the source inductance, as you know, because of the source inductance here, what you can see, like the current is transferred from one set of device to other instantaneously. But as you know, we had already discussed, due to the source inductance this cannot happen. So there will be some slope where let us take the example here. Before this one will start conducting, like the 5 was conducting, like the SCR5 was conducting. So at this moment of time both 1 and 5 will be conducting, and which due to which like this output voltage will be decreased by some amount and will have this kind of a shape. And because of this, and we are already discussed, because of this commutation overlap, like average output voltage will be decreased by some amount, which is will be given by this equation. So what is given to us, like we have at the output we have a resistance is given, output voltage is given, so we can calculate what is the average output at the output. That will be the sum of this E plus what the current is flowing and the R, which will come to 400 plus 20 into 1, that will be equal to 420 volts. Also what we know is output average voltage is given by this equation, which you can see in the notes or what has been taught by the sir, or you can go through those lectures and you will see that this equation and the derivation of this equation, how we got up to this equation. So we have this equation, and in this equation all the parameters are known, and also we know that this average voltage should be equal to like this 420 volts. So here what we will be getting is the alpha. Now once, so when we solve this, put the values here, so alpha value can be calculated, which comes out to be equal to 34.38 degree. Now coming like because of this commutation we are having other equation which can be derived, which is also shown there, and which can be derived by using like equation for the source inductance, LdI by dt equation, and this is the equation that is given here. Once we got the value of this alpha is known to us, also like these parameters are also known to us here, like VAB is here the line voltage, but what is given is the phase voltage. So VAB will be root 3 times the phase voltage. Now these all the parameters are given to us. Now if we put the value of alpha equal to 34.38 degree here in this equation and solve this equation, we can get the value of mu, and mu will come out to be 8.22 degrees, and that is the solution to this question number 6. Now coming to the seventh question. The seventh question is: a single phase fully controlled thyristor bridge AC-DC converter is operating at a firing angle of 35 degree and an overlap angle of 15 degree. So what is given? We have a single phase and we have a fully controlled bridge AC-DC converter, that is a single phase converter, and we have a firing angle like alpha is given to us, that is a 35 degree. Also what is given to us is like overlap angle, that means there is some source inductance, because due to the source inductance there will be commutation or overlap, and that overlap angle is given to be 15 degree, and constant DC output of 20 amps. So at the output we have a constant DC current, that means the output has a higher inductance, which makes this due to which this output current is constant. And what we have to calculate is the fundamental power factor at the input of the AC mains. So we have to calculate the power factor. So we'll take up this question. So here we can see we have a single phase full bridge as is given. Also we know that this can be turned on, these is turned on at an alpha degree. Here as you can see here, it is these devices are turned on, and due to the source inductance the current won't be instantaneously this like this, but it will take some time to rise, some time to rise, and that is given by this mu. So we had already discussed like in the three phase, like the between this, had this been a like a straight, we would not have been this overlap interval. So like this the difference between the fundamental of the current and the voltage would be equal to alpha. Now since we have an overlap interval here as well, as you can see the fundamental of this current is passing through the center of this overlap. So here you can see that the source voltage and the source current like have a phase difference of an angle phi and plus mu by 2. So we can calculate the power factor like will be equal to cos of phi 1, and here we phi 1 can be calculated equal to alpha plus mu by 2. So we know the value of alpha, we know the value of mu. So putting up these value, what the power factor or displacement factor comes out to be equal to is 0.737. So option A is the correct answer to this question. Now the eighth question. Here what is given: a three-phase full converter delivers a ripple-free load current of 10 amps with a firing delay of 50. So here what is given is like we have a ripple-free, that means that at load inductance is very high, and we have a load current of 10 amps. So also the firing angle delay is of 50 degree, and the input voltage is 3-phase 400 volt 50 hertz. So what we have to calculate here is active input power and reactive input power. So we have to calculate the input power, active as well as the reactive power. There are certain options that are given here, and we'll look into it what is the correct answer. As you can see here, coming like similar to the first, this is a three phases given as already discussed, like SCR1 will start conducting from the alpha, and the current will start conducting from this. The source current will be positive when this SCR1 will be conducting, and when SCR4 will be conducting, as I already discussed. And already I had told, like, the phase angle between the fundamental of the current and the voltage will be alpha. Like the center of this will be, this is the voltage where from it is starting, and this is the current, and it will be from alpha, and we know the alpha. Now firstly, what we want to calculate is the RMS. Alpha we know, like the this no. Now what we want to know is the RMS of this cos square wave, and we know the RMS of the fundamental is given by this equation, and here the theta is taken to be 60 degree, and theta is the interval in which this current is 0, and we know this current is 0 for the 60-degree interval period, 60 degree, and it will be conducting for the 120 degree. So here this is 60 degree, and by this we can calculate this RMS of the fundamental, which comes out to be root 6 by pi I out. Also I told you, like, the phi will be equal to alpha. So here we know the active power is given by this equation, and what we needed for this is the A1 is also given, which we had calculated, is given by this equation, and putting the value of the phi 1 equal to alpha, we can calculate the power. So the power will be given by this equation. Here everything is known to us, like VAB is known, I out is known, and alpha is known, and you put the values of this, and the active power will come out to be equal to 3.472 kilowatt. Also for the reactive power, what we do is reactive power is given by 3V I uh, sine of this angle between this voltage and this current, and we know that is alpha, and if we put that value here, and the reactive power comes out to be 4.138 kilowatt. So option C is correct. So here now the question number 9, for a 12 pulse converter with a resistive load, the maximum possible firing angle is. So one thing we know, like some of the student has answered this question, like what we know here is that for the resistive load, the output voltage cannot be negative. For this, like, before going to this 6 pulse converter, I'll to go through this, the question we had already solved for this 3 phase, 3 pulse. This we had seen here, like for this resistive load, if the alpha is greater than this, as alpha is greater than pi by 6, there is some portion of this zero curve. So when this alpha will be equal to like this 120 degree, like from this portion, when, if you can see, when this, when alpha is, when this, if you can trace this waveform of VAN voltage, if alpha is at same at the position of the pi, we won't be having any output voltage, we will be having a zero output voltage. And if the alpha is greater than pi, like for pi, no, alpha is not greater than pi, like if the alpha is pi position of this, for the phase A, we can, then there will be no voltage, then there will be no voltage at the load. So if this is 180 degree, and we know, like, each of this interval is 60 degree, and you can see from the start of this VAN to this point, this is 30 degree. So if the what we can have is alpha if the alpha is greater than 180 degree minus 30 degree, that means alpha is greater than 150 degree, we won't be having any voltage, like output voltage will be equal to 0. Similarly, we can say for this three phase, this 6 pulse, if you can see for this 6 pulse, like this interval is 60 degree, like for this 5 max, this portion, if this phi is like this greater than if you can trace this, if this is greater than like 120 degree, we won't be able to have any voltage for this 6 pulse kind of a thing. Like this red voltage traces are for 1 voltage for the 6 pulse. So when this alpha will be greater than this this is like 60 degree one in this interval, this is 60 plus 60, like this is 120, like if the phi is greater, alpha is greater than this 120 degree, then we won't be having any voltage for the resistive load. Had this been an RL load, like we would be having some voltage positive, or as we will be changing the alpha, we can have the negative or voltage as such. Now coming to the 12 pulses, you can see like this diagram is has like 12 pulses here for the 2 pi interval. As you can see, if we trace one of this waveform from 0 to 2 pi, you can see that it crosses this, like if you can see, like this one interval is like this one interval is around like 30 degree, this one interval is 30 degree, and like alpha we calculate from this point, when this is 30 30, like this whole interval from this point to this red point is 120 degree, and you can see like alpha is from the half of this 30, like this is 15. So you can calculate like alpha max will be equal to 120 minus 15 degree, that will be equal to 105 degree. So if you have an alpha greater than 105, then we won't be having any voltage at the output for the resistive load. That means the maximum of the alpha that we can have is 105 degree, like the option D is correct. Now coming to the last question of today's interaction, like we have a single phase full converter feeds an RLE load whose like parameters are given 5, 6 millihenry and 50 volts, and the AC source is given to be 230 50 hertz. For what we have to see, the for continuous conduction, find the average value of the load current for a firing angle of 45 degree. We are given the firing angle of 45 degree. Like for this average load current, what we need, if we are able to somehow calculate the average output voltage, and if we divide that average voltage by if we divide that average voltage by R, like we'll be getting the output average current. So yeah, you can see here, like this SCR can turn. First, what we want to like see here is where is does this E lie. So since the value of E is very less, so this won't have any effect on this alpha, because like this E will be implemented at this P point. This SCR would have only been turned on after the point when this input voltage will be higher than this this E voltage. So this had been this higher up to this, if we had like given the pulse alpha earlier, before this input will be higher than E, it wouldn't have turned off. But here we are, alpha is greater than alpha is given, like we can have minimum of alpha where this E meets like is equal to this input. So here, since alpha is given, after that we will be having, also we are having a RLE load, so we'll be tracing like we'll be having the output voltage of this shape, and we know that the output voltage is given by this equation, and if we put the values here, the output voltage comes out to be 146.4 volts. Also, what we know that output, we are having some potential at the output, and the average current through, and the output will be like will be having the difference between these voltage, like what we'll be getting at the output minus the E, and that current will flow through the R. And if we put up the values here, like V out is calculated and VE we know to be around like 50 volts, and if you put that equation, the current comes out to be 19.28 amps, and that's the like option A is the correct answer. And this completes like our today's this problem solving session. If any of you have any questions, he or she can ask. If there are any questions, anyone can ask, or any confusion somewhere, you can ask, like I'll make you understand. Or if there are if there are aren't any questions, then we can close today's session. It has already been to us. Any questions? So if there are no questions, like we can end today's session here. Thank you everyone.
Thank you, sir.
Thank you.